여기 좀 뜨는 거잖아. 여기 이제 나오는 거 유튜버 같이 나오는 거. 그다음에 요거가 이제 이렇게 딱 잡히는 것이. 이거 왜 안 잡히지? 이 마우스가 너무 커져서 깨졌나 보다. 잠깐. 또 빅 미스테이크 또. 잠깐만, 나 이거 셋업만 해보고 되는데. 됐다. 네. 뭐 바로 안 들어가도 되죠?
네.
이거 좀만 놀다 손 맞춰서 올라오면 돼.
그럼 파일은 좀 이따 어떻게 저희가 받으면 돼요?
파일은 제가 저기 그 유튜브 링크를
예.
비공개 링크. 그럼 그걸 다운. 내가 다운을 받아가지고 그 링크를 줘. 피보다는
네.
써도 있어. 여기 있으니까.
팀상으로 시스템 있죠.
아예 싹 바꿔가지고.
많이 바꾼 건 아니고요. 네, 이제 토산하고 이제 수평력 정도 추가를 해서 이제로 또 예측하는 시스템으로 뭐 바꾸는 거에 되게
지금은
간단해졌어요.
포션 못 잡.
네.
여기서 지금 이게 달라져 지금 이 말을 하고 이 그리고 지금 NX하고 NY.
네. 그 제가 3,000인가 3,000 프레임 스트링을 다 고르는 것이 않고 1차원적으로만 이렇게 한다고 해서
1차원?
그러니까 이제 평균 에브리지 스트링
이건 뭐지?
이게 타오면은 이제 토션이 가운데 들어가고 그 토션하고 수평력만 고려를 했을 때 수평력 X축 수평력하고 Y축 수평력 가진다고 했을 때 그걸 이제 슈어 스트링 변화하는
근데 슈어가 안 커.
네.
거의 없어. 그러니까 이거를 이렇게 다리에 내게 있을 때도 포션이 발생하긴 하는데 지지가 이런 식으로
네.
이 자체에 대한 포션.
추가하는 거에 대한 의미를 두고 제 주 목적이 이제 수치적으로 그냥 검증을 하는 체계를 만들고 게이지 설치 위치 같은 거.
여기까지는 지금 내가 좀 만들었고.
예. 그 다음에 이제 그냥 수치에서로만 그냥 시뮬레이트된 데이터 생성을 해서 그걸로 역으로 검증하는.
만약에 다 사각형이면
네.
사각 파이프 이거는 디테일링 때문에 예 사각 파이프는 이렇게 디테일링이 있는 거죠. 이때는 원형을 다 이때는 휘마고 이때는 포션이 중요하고.
그래서 지금 그냥 예시로만 하고 있는 거.
여기 팔을 이렇게 싹 바꿔보거든요.
네?
팔을 이렇게 싹 바꾸고. 근데 여기까지가 썸띵 배우는 거잖아. 그 다음에는 그렇지.
네.
그 다음에는 스트레이 나오면 스트레인 한번 맞춰보고.
네. 근데 이제 실제 데이터가 없으니까 수치적으로 프렌치를 해서
그래. 이렇게. 어제 관입 해석까지 좀 했는데
그럼 관입했을 때 어떤
그러니까 파워포 보고 그러니까 이 얘기가 나오려면
네네네. 제가 지금 소시원이 그래도 조금이라도 실제 상황한테 잡히지 않을까 이거 생각하고 있어요.
그러니까 이끌어도 내용
막 내려가다가 이제 암석 같은 걸 만나게 되면 참 조금 들리죠.
그러니까 모멘트
네.
포션에
그렇죠. 네, 모멘트긴 한데 이제 암석이 교묘하게 두께가 생기다가 확률적으로 생기는. 근데 관입 관련해서 기다리시는
그러니까 지금 여기서 이렇게 들어가는데 그 말대로 이렇게 소위 하드하게 됐을 때
네.
얘가 다르고 멈췄을 때 아니었을 때 그래서 모멘트가 얼마나 그리고 이 얘기를 하고 이거가 많이 들어가니까
예, 예.
지금 우리가 이 얘기하는 건 모멘트가 꽤 크면 위험하다.
네.
그 얘기를 하고 싶어요. 그리고 이제 이거를 마냥 크게는 할 수가 없고 마냥 작게는 할 수가 없잖아. 왜냐면 얘는 지지가 안 됐거든. 얘는 지지는 되는데 얘가 위험하고 그래서 중간에 탈거할 수밖에 없는 건데 그냥 이렇게 운용하다가 과대 모멘트가 안 나오고 그런 측면을 해야 되는데 이런 상황에서 그런 여기 이 얘기 보면 집안 전체를 뚫고 지나가는 거는 원래 묻혔다고 가정했을 거고 그래서 스몰 디펜 아니면 아바쿠스에 AL이
네.
근데 그거는 뚫고 지나가니까 우리가 요소가 다 터지고 컨버트 인플리스가 컨버트 관리되서는 안 될 거고 이체 흑 물성은 어떻게 이거는 나도 이거는 이종석이나 체계다. 근데 전에 그 거덜 그 해놓고 왜 그냥 그게 멍청했었다.
두 번째 안이 저 예전에 최적 담론 공유
그렇지.
가운데 웹 부분 이렇게 해서
그것도 있고 이번에 다시 또 써질 뻔했어. 그 공급비하고 그래서 그 전에 앞에 2차를 한번 써놨거든. 그게 쉬고 이거는 너가 재밌어. 이거는 썸 모음이 아이돌 웨이 있어.
처음부터는 제가 공부하기 싫었어.
그래? 알았어. 다음 사람도 지금 챌린징을 보고 있어. 지금 이걸 설계를 어떻게 할 건지. 이게 지금 이해를 한 다음에 그 다음에 이게 쉘파이브도 이거 하겠네. 근데 얘하고 얘는 달라. 얘도 뭐. 알았어. 괜찮아. 어느 쪽으로. 좀 이따 쏠거예요. 긴 일도 아니구만. 그렇게 쓰는 것이다. 야, 하기 좋은 것만 한다고 하면은 할 거 하나도 없어요. 나 하는 것도 안 하고, 나도 하기 싫은 거 하고. 아까 안 하고, 이것도 안 됐지. 파일 관리되는 거지. 지금 내가 아까 한 전화 받아서 2분 만에 뉴폰 파일 체크 훨씬 하다 보면 솔직히科目에서 어려운 게 얼마나
자유낙하에서 이제 관입되는 깊이만큼을 에너지
너무 쉽지. 원래 지금 지방쪽 원래 지금 운동 에너지 뭐죠? 이거 참 날려갔고 속도가 굉장히 올라.
여기다 어딘가에 중간 속도에 대한 내용만 살짝 딱 들어가면은 괜찮을 것 같아.
아니 없어. 속도가 안 필요해. 여기다가 그 자유낙하 할 때
그래프스가 좀 지배적이게
앞으로 자유낙하 계산할 때 이거
이게 수면이 여기
아니 여기가 수면이고 여기가 딱 이만큼 이만큼 딱 꽂히는 거야. 이게 딱 지지력 계산하는데 지지력이 있으니까 굉장히 지그지. 예, 알겠어. 네, 어서오세요. 좀 보자. 이제 수업 하려고 근로계약서고 근로계약서는 지금 업무용 관리 쪽으로 써도 되겠고요. 그다음에 포괄 임금제에서 기준에 보면 잠깐만 나오게 그것도 월 되고 그다음에 이제 월급에다가 비과세 항목 식비하고 시간을 잡을 수가 있어요. 그만큼 그러면 요청을 해냈고 그다음에 임금직으로 25일 정도 되고 휴일이면 정일직을 보고 아니면 내가 출장을 가면 어쩔 수 없이 대부분 다 임금직을 보고 있어요. 그다음에 이제 출장하고 성과급 규정은 임직원들이 다 가지고 있어요. 그래서 뭐 연애 마커시 15분 마커시 최근 X 마커시 아마 20% 정도가 이거 원공 일에 추가되고 있어요. 그다음에 이제 연차이고 많은 여성분들이 모르는 분도 계셨고 그다음에 이거 말고 지금 유진연봉 이전을 해봤는데 실제로는 한 달치 그걸 가지고 있어요. 그래서 이게 12분의 실제 이제 유성연치가 받는 돈은 2,200만 원. 이건 그 세입금 규정에 따라서 1년을 근무해야지 내 회사 돈을 받을 수가 있어요. 그렇지 않으면 세입금 다시 받을 수 있어요. 이게 그렇게 쓰고 그다음에 정말도 다른 거 말고 회사에서 취직하는 거 비밀로 취득해요. 부담은 아직 없으시죠? 그럼 사인 사인 그렇게 하고 정보 보호자 하시고요. 이거는 잘 판단해서 네. 사책이 이름 잘 찍혀있고 근데 보니까 집이 그냥 가깝더라고요.
네.
근데 너무 가는다. 오, 오늘 지금 학교가 있어요.
혹시 헬로윈 목요일 그래서 헬로윈 목요일 날에 왔거든요. 그래서 무료가 들어가지고
아, 슬퍼. 그거 꼭새 유소 오면 한 번씩 그거 너무 좋아하겠다. 오빠한테 네. 할로윈 모델이 안 되는 거예요? 네.
too dark. Hello everybody. Before we start today's lecture, may I have questions from you? Last time we discussed the torsional problem. We found close similarity between uniaxially loaded members and the torsional members, isn't it? In the case of uniaxially loaded members, the so-called elongation is equal to the length divided by the elastic modulus and the cross-sectional area times the internal force, isn't it? But in the case of torsional problem, the angle of twist is equal to length divided by the shear modulus and the polar moment of inertia, and then internal torsional moment. So last time I told you that this is what? This is elongation. What is elongation actually? The elongation means displacement difference, right? Elongation means displacement difference. Okay, that's how we measure. For instance, so if you have a coordinate, if you choose this coordinate system, the elongation of a bar occupying in the region A and B. So then to calculate the elongation, we need to subtract nodal displacement of point A from the nodal displacement of point B, isn't it? not this one, isn't it right? We don't call it elongation. So this is elongation. That's how we define it. And then please make sure that this is what? This is, we call it angle of twist. So angle of twist is, you know, similar to the elongation of uniaxially loaded bar. This is what? This is twisting, the difference of twisting angles, isn't it? So of two nodal point actually. Is it clear? And then this guy is what? So this guy should be the internal force. Internal force. So this is not an external one, okay? So please make sure that this is very important. This is the internal force. And then what is this? Is this internal or external? Now, what is your choice? External or internal? What's your answer? Internal or external? Hi Justin, what do you think? 예원이, what do you think? Is it internal or external? Internal, okay, great. So you understand. 훈이, what's going on with you? 훈이, what's wrong with you? Why do you think it's external? Yeah, you'd better explain why you are thinking, you know, that torsional moment is external. So please make sure that this is internal, okay? So I emphasize you many times, this is internal, okay? This guy internal, and then also this guy is internal, okay? Yeah, Sumini, you are also correct. It's the internal torsional moment, okay? Internal torsional moment. And then what is the right sign convention for the internal force? The right sign convention for the internal, for example, in the case of uniaxial loaded members, okay, I accept. And then the positive internal force, positive internal normal forces is defined as this, okay? So the reason that we are doing this, the internal force is kind of integration of stress over the cross section. That's why the sign convention for the normal stress is what? If the material is stretched by the stress component, then we'd like to define it, this is positive stress, isn't it right? Positive state, sorry about it. And then similar to this, if you integrate this normal stress over the cross section, then we can obtain so-called internal normal force, okay? This is sign convention. And similar to this, for example, in the case of torsional moment, internal torsional moments, if you follow the right hand rule, okay, then we'd like to define this is positive torsional moment, okay? So please make sure that if you set up a coordinate system like this, so if you set up a coordinate system, then with respect to this coordinate system, the pair of internal force has two different components. So this guy is heading the positive direction, and this guy is heading the negative direction, isn't it right? Okay. So this is internal. So we use this sign convention when just before we check the force equilibrium compared with the external forces. Okay. and then the remaining the solution procedure is exactly same as before. Okay, don't worry about it. And then what you have to be careful is you have to distinguish the difference between the elongation and the nodal displacement. And similar to this elongation, this is angle of twist, and that represents the difference of twisting angles of two nodal points. Okay, this is really important. And make sure that in this formula that represent the internal force. The torsional force, these torsional moments are also the internal torsional moment. Is it clear? And that's what we discussed last time. And then the last time we discussed the development of the stress, isn't it, right? Development of stress on the surface of torsionally loaded members. And then I also told you that, so if you consider torsional arbitrary cross section, for example, let's consider rectangular cross section. Then if you consider a torsional loading to this rectangular cross section, let's say this end is supported. Not supported, sorry about it. Let me take it out. Okay. Sorry. So rectangular section. And then we'd like to provide a coupled torsional moment. So this side in this direction, okay? So what happens if you do this? Then because we have warping, so-called warping displacement, so this corner comes out, and this part is comes out and comes in. So we have warping displacement. Okay? So which means the plan before deformation doesn't remain a plan after deformation. That's the problem, okay? So for non-circular sections, there exists warping. Okay? So that that make problems very complicated. That's why in our classrooms we do not consider the arbitrary section except the circular sections. Okay, the circular sections are only sections in which there is no warping displacement. And because of this warping problem, when you consider non-circular sections, we have to use a special formula to consider this warping effect, okay? So let me skip it because the subject of warping is advanced subject. So anyway, what you have to see is if you look at the formula or the further calculation of angle of twist, for example, look at this. Say, the length is the same, the shear modulus is the same, but instead of polar moment of inertia, we use so-called J rectangle. Okay, if you look at J rectangle, it's pretty much different from the polar moment of inertia of the cross section, isn't it? Okay, today let's talk about thin walled tube. By the way, I didn't tell you the energy stuff. So last time we also talked about the energy, using the torque and then angle of rotation, isn't it right? So I told you that the lower part of this curve is called deformation energy, and then upper part of this curve is complementary energy. So only in the linear elasticity, the numeric value of the deformation energy and the complementary deformation energy is the same. But if you have a nonlinear problem, then these two values are not the same as each other, okay? Only for the linear elasticity. Actually, the writing in this way is wrong, actually. We shouldn't do that. It's not a good habit. This part is the deformation energy, okay? Where is it? This part is deformation energy. So I told you that this is what? For linear elasticity, it's a complementary deformation energy. Because when we calculate deformation energy, the control variable is what? The angle of twist. when you calculate complementary energy, the control variable is torsional moment. Do you have any questions? Is everything clear? Alright, so now let's talk about thin walled tube. Okay, actually if you look at this thin walled tube, you know, the cross section is not circular. So you may ask me, you may have questioned that, well, because the instructor just mentioned that for non-circular sections we have warping deformation, then we cannot use the formula that we discussed so far to this thin wall tube. Yeah, your question would be should be correct. Okay, we cannot use that. But last time I also told you that to prevent warpings we put diaphragms in regular spacing. So if you put diaphragm, then we can you know, restrain the warping deformation. So only when we have restrained warping deformation, so we can use the thin walled tube formula. Okay, so let's consider a member. Let's consider a member. Okay. Thin walled member. And the thickness is changing like this. So here we have thin section and then we have thick sections. Okay, and then say it is subjected to certain kind of torsional moment as given here. Then look at this. So if you detach here, if you consider small materials, so I want to look at it in detail. I'll look at it closer. Okay, because this part is subject to the torsional moment, let me use the circular section. Curvy section. And then because of this twisting moment, then we must have this shear stress here. Okay, if it is so thin, then the direction of the shear stress would follow the direction of the length of the cross section, isn't it? Okay, and then if you look at even smaller corner, for example, I want to look at very small corner here. So if you look at very small corner, let's consider we have very small material point. So please imagine, please recall your memory. So if you have any shear stress, if you have shear stress here, tau, to satisfy the equilibrium of momentum, angular momentum, so we must have the same shear stress in the normal direction, in the tangential direction like this. Otherwise we cannot satisfy the force equilibrium and then the angular momentum, isn't it? So which means, so let's say I want to choose this is point B, and I want to call this is point C. And then let's say at this point we have, say for example, at this point we have shear stress tau B, and the thickness is thin compared to the size of section, so we may assume that the shear stress, magnitude of shear stress is constant over the cross section, over the thickness, isn't it? And also here I have tau C, isn't it? But if you look at this, argument, isn't it? If you look at this argument, so I have, because of this, I must have exactly same magnitude of shear stress, but in the tangential direction, isn't it? At point C, the lower part of point C, we have another shear stress its magnitude is equal to tau c to satisfy the force equilibrium condition. On the top of point B, we must have, you know, the tau b in this direction. Is it clear? Okay. So here we consider pure, you know, torsional problem. So the internal torsional moment should be same everywhere, isn't it? So we must have same stress state whether we cut here, 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 isn't it? So which means here we have same shear stress tau c, also tau c, blah blah, isn't it? And then on top of this member we have tau b. Do you have any questions? Okay. So okay, and then to simplify the problem, I want to multiply the thickness. I want to multiply the thickness to the shear stress value. So instead of, you know, playing with the shear stress itself, so I want to multiply the, I want to integrate. Okay, so I want to integrate. Then at point B, FB is equal to tau b times the thickness at point B, isn't it? And then also here I have, at this point, I have FC is equal to tau c and thickness at point C. Okay? And then because here FC is constant, because tau c is constant on the bottom, so here we have FC is constant, and the FB is also constant here, isn't it? So if you integrate FC, how do you calculate FC? The capital FC, then FC times the length of the segment, isn't it, right? Length of the segment is dx, isn't it? And then also the force FD, capital FB here, FB on top is FB is equal to FB times dx. Is it clear? Okay. And then the FB is here. We have FB here and the FC here. All right. And then let's check the force equilibrium. If you check the force equilibrium for this problem, sum of all the forces in the horizontal direction should be equal to 0. So according to this sign convention, FC minus FB should be equal to 0. Then what do we have? Then FC dx minus FB dx is equal to 0. And then here dx may be cancelled. So we can conclude that the FC measured, the shear stress times the thickness measured at point C is equal to shear stress times the thickness measured at point B, the same. Because we haven't fixed the specific point, this is the given value F. This is constant for the cross section. So F is kind of constant at the section, Is it clear? And this quantity is called shear flow. It is defined as shear stress times the thickness. Okay, so if the shear flow is constant, for example, at a point where the thickness is small, then the shear stress should increase. If thickness is big, and the shear stress decreases. Yeah, that's exactly what we can expect. Okay, so now let's talk about the cross section. Let's say if I redraw this cross section here. Okay, let's try to redraw the cross section. And then I have thin part, thinner part, and I have thicker part like this. Okay, and then let's imagine a middle line here. Jungu, actually look, if you look at the shear flow, if you look at the formula, shear flow is shear stress times the thickness. Then what does it mean? The unit of shear stress is unit of force divided by length square, isn't it? And the thickness is what? Just the length, which means force and then length to the power minus 1. Okay, is it clear? This is the unit of shear flow. You're right. And then let's follow the middle line. Okay, so as we discussed, following the middle line, we have shear distributed shear flow, F. The F is constant. Okay, so F is constant. So now this is the centroid of the section, and then let's imagine. Let's imagine this guy. I have shear flow. I want to consider this small segment, ds. Okay, so as Jungu, like Jungu's question, the unit of shear flow, the dimension of unit of shear flow, the unit of shear flow is force per unit distance. So which means it's not a force yet, isn't it? That's why to make a force, let's imagine I want to calculate this force here. So if I want to calculate this small force, dF, then how do you calculate this dF? Because the unit of this force is what? The force per distance. That's why we have to multiply the length, isn't it, right? The shear flow times ds. Then this is what? The force per unit distance. That's why if you multiply the length unit, it becomes force. Okay, that's how you can obtain it. And then now I want to calculate the torsional moment. The small torsional moment caused by the small force is equal to what? The force times the arm length, isn't it, right? Yeah, this is a definition. Okay, so then how do you define the arm length? The arm length is the close distance to the path of the load vector, isn't it? So that should be the arm length. Okay, this is arm length. I want to call this as arm length R. So this is equal to arm length R times dF. So if you plug the definition of small force dF here, this is equal to F times R times ds. Is it clear? Alright, Then we calculate the contribution of the small force to the torsional moment. We just calculated the small torsional moment, and then we repeat this job everywhere. So following the perimeter in the entire cross section. So we do this. So which means to calculate total torsional moment is sum of all the small torsional moment. Is it clear? Then what does it make sense? Then this is equal to what? Because now I have the shear flows continuously, which means I can change the summation sign to integration dt, where over the entire path. Okay. Then if you do this is, let's plug in here the integration over the entire path, and then I want to consider the shear flow and then the arm length dr r times ds. Now please make sure that the shear flow is constant for the cross section. That's why we can take out the value of shear flow from this integration, s r ds. So let's look at the formula carefully. So if you look at the formula carefully, so we have very simple geometrical relation. Say this is ds, okay? This is ds, and this is the arm length r. It's like what? It's like, for example, let's imagine I have a triangle. Let's say I have an equitriangle, and then let's say the width of triangle, bottom width of triangle is given by ds, and its height is given by r. We can imagine it this way. So it's kind of analogy. Now how do you calculate the area of this small triangle? The area of a small triangle is equal to dA is equal to a half of what? R times ds, isn't it? So instead of r times ds, we can plug this value here. Then the torsional moment is equal to shear flow, and the integration, instead of r ds, we have 2 times dA. Now the integration operator has been changed from the perimeter to the area. That's why it becomes the area integration. That's why it becomes 2 times the shear flow. The area integration is nothing but just the area itself, isn't it right? Then we can derive a formula, torsional formula for thin wall tube. The shear flow can be calculated from the applied torsional moment divided by 2 times the area of the section. Make sure that this area represent here. The AM is for this. This is AM. Okay, this area stands for AM. Do you have any questions? So once you calculate the shear flow, then depending on different thicknesses, then we can calculate the shear stress at certain point. For example, if you want to calculate the shear stress at point star, then we have to divide, this quantity by the thickness at point star. Is it clear? Okay. And then this is rather a little bit advanced subject. For thin walled tube, yes, we can apply the angle of twist formula. Sumini, yes, we may choose the middle line. You can take the middle line as the boundary of the cross section AM. But typically when we deal with thin wall tube, actually the thickness is very small compared to the size of the section, and we can neglect the difference. But generally speaking, you can take the middle line. Yes, middle line as the boundary for the calculation of AM. Yes, good question. And then instead of polar moment of inertia, and we use J here, and then we can calculate J using this formula. It's worth of memorizing. Alright, similar to the uniaxially loaded members, we have stress concentration even in torsional problem. We never connect two sections with right angle. We don't do that actually. So we draw our problem in these ways only for the simplification of a certain kind of idealization. But we never fabricate our structure in this way. Okay, we don't do that. Okay. Instead of that, we introduce some, the fillet round transition here. So with this, depending on the radius of this fillet round, we have different values of the stress concentration. So what we do is we calculate the shear stress as if we do not consider any, stress concentration. Depending on the geometry, we calculate the stress concentration factor, and we multiply the stress concentration factor to the value. Is it clear? Okay. Now here's a summary. Okay, in chapter 3, we discussed torsionally loaded members. And although the torsionally loaded members, if you discuss torsionally loaded members, we have the shear stress distribution. But the structure of Shortcut formula in member level, and their Shortcut formula is very close to that of the formula that we discussed in the chapter for the uniaxially loaded members. They are very similar, isn't it? So as I showed it here today. Look at this. Okay, these two formulas are really similar to each other. Okay. And then here are your homeworks. So we have some of homework problems. Please submit your homework in 1 week actually. So because next week we're gonna take the midterm examination. That's why you can submit your homework next week if you want. Because we are talking about officially 1 week. All right. Let's move to chapter 4. By the way, do you have any questions before I close this lecture note for chapter 3? No questions? All right. 주승이, is the range for the midterm examination up to chapter 3? What? What do you want? Huh? What do you want? Do you have any suggestion? By the way, it doesn't come up. Hold on a second. Surprisingly, it doesn't come out. Hold on a second. Okay, sorry about it. 수민이 well 3단까지 usually I take midterm examinations or the final examinations up to with discussed before the midterm, before any examinations. That's my rule. Okay, so let's move to chapter 4. The chapter 4 is for beam problems, the shear force and the bending moment. Alright, so starting from the uniaxially loaded members and then torsionally loaded members, we use the three conditions, isn't it, right? We use the three conditions for any kinds of problems. So now we move our attention to the beam problems. So although we are talking about different subjects, the rule is still same, so no change, okay, no change. We want to still use the same three conditions to solve our problem. The same again, so we have kinematic constraint, the kinematic constraint between the displacement and strain. And once I have, if you follow the blue lines, once we have the strain, information of strain, using the material load we calculate the stress, and then using the stress we check the static equilibrium. That's how we finish our calculation. Or we do the same jump from the static equilibrium following this purple line. And first we calculate stress, and then from the stress we calculate strain, and then from the strain we calculate the displacement. And then we have different scales. So these scales, that scale represents a structural scale, okay, structural scale. The structure contains the material points too. And then member level, this is a member level. So we sometimes we deal with internal forces instead of the stress value. So we instead of talking about the stress and strain, so we can play with the internal forces defined for different structural members, like normal forces or the internal torsional moment, isn't it? And then at the material point level, so we use this material law. So you can calculate the energy, isn't it, right? At structural levels, we have we can calculate the work done by the external force. And then at material point levels, so we have work density, isn't it? So if you consider work equilibrium, so work done by the external force should be equal to, the deformation energy. Deformation energy. Sorry. Okay, so deformation energy. So deformation energy is defined as given in your textbook, integration of deformation energy density. So make sure that deformation energy density is defined at material point. So we have to integrate it over the volume. So here the omega stands for the domain. So it's like, the volume as given in your textbook. And then here, deformation energy density, this is deformation energy density. Energy density. Deformation energy density is defined at each material point. Okay, each material point. Then how do you calculate the deformation energy density? Deformation energy density is defined in this way. This is the work done by the stress over the strain, isn't it? But in the case of one-dimensional Hooke's law, the stress is given by the elastic modulus times strain. So if we plug in here, This is given by elastic modulus strain 0 to the strain value. Okay? And this is equal to a half of elastic modulus and the strain square. And similar to this, for the linear elasticity, the complementary differential energy density is defined by stress sigma square. So make sure that the control variables are different. In the case of when you calculate the differential energy density, the control variable is strain, and when you calculate the complementary energy density, the control variable is stress. Okay, this is key difference. Do you have any questions? So here we have learning objectives. What we want to do is we want to discuss so-called beams and frames. Okay, that's what we want to discuss. And once we have ideas on the beams and frames, we want to study so-called then what kind of internal forces that we use. Now here the internal forces for beam problems that include internal moments too. So although here we discuss internal for beam problem, so we talk about internal forces, and then but in general sense internal forces include internal moments too. In general sense we call these internal forces. Okay, sometimes we denote only the forces using the terminology of internal forces, but sometimes in general sense we consider both forces and moments. And then we want to talk about the types of loads applied to the beam, and then we have support conditions for beams and frames. And then we want to discuss the governing differential equations for beam problems. We want to discuss so-called axial force diagrams and then shear force diagram. So please, we want to discuss 3 different concepts. Sorry about it. AFD, SFD, and then BMD. This is a really important terminology, and this is axial force diagram, and this is shear force diagram. This is bending moment diagram. Okay, so among these 3 diagrams, maybe you shouldn't forget about, you cannot work with these 2 diagrams, shear force diagram and bending moment diagram, before you retire. This is really important. Shear force diagram and the bending moment diagram. Okay. All right. So now let's talk about what beam is. What is the beam structure? The beam is defined as structural members subjected to loads in the lateral direction. Say we have, let's say we have one-dimensional structure like this. For the same one-dimensional structure, like one end is fixed, is supported here on the left-hand side, and then if this beam is this one-dimensional structure is loaded in its longitudinal direction, this is a longitudinal direction, we have loading in this way, then we call it bar. Okay, we call these structures bar. But if you have load rather than the load in the longitudinal direction, if you have load in the lateral direction, then the same structure is called beam. Okay, by the loading type, so we call the same structure using 2 different names. Sometimes it is called bar, Sometimes it is called beam. And then if you imagine the deformation of the beam subjected to this lateral loading, then once we have this load, probably this beam, this structure would deform like this. Isn't it? Yeah? It will deform like this. By the way, beyond the loading point, there should be straight line. Sorry about it. Okay? So the deformation of the beam, takes in place on this plane, isn't it right? So on this plane, not the outer plane, isn't it? So the plane where we can imagine the deformation of the structure is called planar bending. Okay, planar bending. And that bending is called in-plane deformation. This is called in-plane deformation. In 우리말 면내 변형. Okay, so 면내 변형. Do you have any questions? Then now let's talk about the loading type. So we may imagine four different kinds of load. So first we have, as given here, so we have concentrated forces. Concentrated forces. And then also we have concentrated moment. So in this case, the force is concentrated at a point, okay? And then in the case of concentrated moment, the entire magnitude, the force is concentrated to the loading point. So we call that concentrated forces and concentrated moment. 우리말 집중 하중. 우리말 집중 moment. Similar to the shear force. So if you define the force as force per unit distance, then we have distributed force. So here the force is distributed over a certain region, isn't it right? So we call it distributed force. 우리말 분포 하중. And then actually the magnitude of the distributed load may depends on the distance. For example, we can define the linearly distributed load or quadratically distributed load. For example, the distribution can be linear or can be quadratic. Yeah, any shapes. So if the distribution is uniform, if it is uniformly distributed, what I mean is magnitude the same over the loading area. So we call it uniformly distributed load. In 우리말 등분포 하중. 등분포 하중. Is it clear? Okay. So we have several different types of load types. And then also the moment too. We may imagine distributed moment too. Alright, so now let's talk about the types of beams. Actually, we classify the beams, by the support type. For example, Let's imagine I have a bar here or a beam, say, because now we want to talk about a certain load conditions where we have load in the lateral direction of this structure. And then if you don't provide any support here, so that allows rigid body motion, isn't it? So here my target is I do not allow any rigid body motion of the structure. For example, if you put a hinge point here, then actually if you put, because I put the hinge point, maybe this structure cannot move in the translation, you know, in the longitudinal direction or in the vertical direction. It cannot do that, but instead of that it can rotate. So we have another rigid body rotation, isn't it, right? So to prevent this, then I need to put another point here. Then we prevent any rigid body motion. So we want to provide a rigid body motion. We want to prevent any rigid body motion. Why it is important to prevent the rigid body motion? Because of this. So we want to use the sum of force should be equal to 0. Do you remember I explained you that the sum of force is not equal to 0 according to Newton's law? Newton's law, sum of force should be equal to mass times acceleration of structural system. So which means, you know, if the body moves with constant speed in which the acceleration is equal to 0, still we can satisfy the force equilibrium. Sum of force is equal to 0. Okay, so it doesn't guarantee the stationary system. To have the stationary system, so we need to prevent the rigid body motion. Okay, all right. So let's consider 3 different types. For example, I have beam, and then one end is fixed. So obviously there is no rigid body motion except any deformation caused by the load, isn't it, right? So we call it cantilever. Okay, cantilever beam. In 우리말 외팔부, or simply we call cantilever. Alright, or I have a beam, and at one end we have a hinge support, so it allows rotation but no translation. Okay, and then at the other end we have roller, so it allowed, you know, displacement in the longitudinal direction, and it also allowed rotation too. So no rigid body motion here. Okay, so we call it simply supported. Simply supported beam. In 우리말 단순 지지보, or sometimes we call it 단순보. Is it clear? Okay. And then now let's talk about the type of support. And then this support is fixed support. In 우리말 고정단. And how about here? This is free end. In 우리말 자유단. Okay? And obviously here no rotation, no longitudinal displacements, no vertical displacement. And how about free end? At free end, yes, free rotation and then free displacement. That's why we call it free. And this guy is called hinge. Hinge support. In 우리말 hinge. And then here rotation, yes, but no UX, no UI. Okay. And how about here? We call it roll. In the case of roll, no vertical displacement. It allows displacement in longitudinal direction, but it allows rotation. Here, let me take a 15 minutes break.
아, 말씀하세요.
지금 쉬어요. 몰라. 연락이 없더라. 그래서 제 연락이 없어. 거기 부럽 잡아놓자. 유니사선 더 딴 얘기 없지. 근데 왜 다르래? 뭐를? 물어봐. 그냥 간단하게. 뭐, 물도 그래. 이건. 근데 그럼 우리 엔지랑 다 그렇잖아. 그러면 그 복수충이라고 해서 그럴 때지. 그렇게 뭐가 그럼 아니 우리는 그거 뭐야? 그 설명. 아니 우리는 그거 그렇죠. 그 엔지가. 우리는 그뭐 내가 저거니까. 여보세요? 근데 보면 그 120에서 180이 되면 물량이 1.5배가 되는 거예요. 그죠? 그러면은 저기 어차피 뭐 레미콘으로 할 것도 아니고 그거 저기 불꽃이나 그 프리팩 사다가 할 거잖아. 그럴 거 아니야? 그러면은 믹서 50% 나갔다 놓고 하면 되잖아. 근데 그것도 뭐 한쪽에서 다 해가지고 원형 다 채울 것도 아니고. 그러니까 두세 개를 연속적으로 할 거면 50%더 쓰라고 그래. 아니 그건 개수를 더 쓰라고 그러면 되잖아. 그거 괜히 안 된다고 하지 마. 처음에는 블리딩 때문에 안 된다고 했는데 이건 아니고 그렇게 얘기를 해줘. 그렇잖아. 그러니까 지금 기껏해야 뭐 10배 늘어나는 것도 아니고 1.5배 늘어나는 건데 바로 그거 프리팩 써다가 하는 거야. 딱 아는 척을 해줘. 어차피 프리팩 쓸 거 아니냐. 프리팩 쓸 거면 그렇지. 그 어차피 그 섞어 믹서하고 그런 거 있으면 되는 건데 그거 보고 한 50% 정도 늘려고 하면 왜 문제야? 그래 딱 얘기해.
아, 현민이. 예스, 그럴 수 있지. 야, 나도 사람인데 틀릴 수도 있지, 야. 맞아, 내 기억에 옛날에 그런 거 하나 있었던 것 같아. 아니면 기출문제 풀어봤으니까 very nice. 기출문제만 잘 풀어보면은 성적 잘 받을 거예요. 나는 공정한 게임을 위해서 기출문제는 항상 공진해줘요. 어때요? 기출문제 공지해줘가지고 싫다는 사람. 동현이, 조교가 배포할 건데, 내 조교한테 이미 배포해라고 했어요. 내가 조교한테 다시 제시할게요. Alright, do you have any questions? So for equal opportunity, usually I distribute my previous exams. 체린이, the subject for the midterm examination must be fixed after today's lecture. Just up to what we discussed today. Clear? Alright, so let's go back to class. So I discussed the types of loads and the reactions here, the types of loads, and we discussed concentrated loads. So if you have inclined force, so for example, So let's consider a situation that, so we have, oh, let's change the color to the black one. So we have, you know, one side is fixed, I have a structure like this. And then let's imagine we have this coordinate system. So we have load in this way, for example. And then let's say it is inclined by angle theta. Then if you still, and then its magnitude is force F. Yes, Sumini, yes, you are correct. And then this is equal to what? If you understand the concept of principle of superposition, 중첩의 원리, then the current situation can be decomposed into what? Two different situations. For one is what? So we have the load in the horizontal direction. And the other case, so we may consider the force in the vertical direction. Okay, and its magnitude, if you understand the vector decomposition, its magnitude is equal to force F times sine theta. And then the vertical load is what? Force F times cosine theta, isn't it? And then how do you analyze this problem? For this problem, so we use the bar, you know, bar or uniaxially loaded members, isn't it? And then for this problem, because the load is in the lateral direction, this is a beam problem. Is it clear? Alright, so now let's talk about stress development in a section of a beam. So let's consider a cantilever here, because its cantilever is so simple. So if you look at a cantilever and we have two different loads, for example, one concentrated load in the vertical direction, the other one is concentrated moment. Okay, and then we want to look at this small segment. Okay, let's look at this small segment. Alright, so we have the same set of external forces. The one concentrated force, the other one is concentrated moment. Alright, so anyway, we want to satisfy the force equilibrium. The sum of force should be equal to 0, isn't it right? In the vertical direction. Say, let's imagine we have shear traction on this imaginary surface. Then we can find the distribution of, we can determine the distribution of shear traction, which is satisfy the force equilibrium, because my concentrated force is downward, and then my distributed load is upward. So if you choose the magnitude of distributed shear traction, then we may satisfy the force equilibrium in the vertical direction, isn't it right? Alright, so on a section we have two different kinds of traction: the normal, stress, and then the tangential one. This is shear one, isn't it? So we already have the shear traction or shear stress, isn't it? And then let's consider another one. If you consider the moment equilibrium, so I have moment here. To satisfy the moment equilibrium, so we need, rather than this shear stress distribution, we need another component of the traction, so normal one. So you may consider the arbitrary distribution of normal stress. For example, let's consider, say, I have 10, okay, as a concentrated moment. Then to satisfy the moment equilibrium, we may have, for example, okay, let's say we need the size, otherwise we cannot work with this. So 1, and how about, let's consider, let's say it's 4, sorry about it. And then So we may consider this normal stress distribution. And then to the middle point, this is equal to 3. And then if you look at only this point, okay, this is a reference point, then probably we can determine the normal stress, isn't it right? So which produce same amount of the normal, same amount of the concentrated moment. We can find anyway. So also we can consider another set. For example, let's say the combination of the two direction of normal stresses. Also, we may find the magnitude of normal stress which produce same bending moment, isn't it right? We can do that. So there are numerous sets of normal stress distribution which produce same concentrated moment. We have another condition. The last condition is, because there is no horizontal force, sum of horizontal force should be equal to 0. This is another one. So to satisfy this condition, the sign of normal stress sometimes, is going to the left hand direction. At some position it goes to the right hand direction, so that they cancel each other. Is it clear? Do you have any questions? Alright, so now we discussed the types of the traction on this surface. Okay, so we must have so-called shear stress. Okay, the shear stress. So if you add up all the shear stresses over the section, the integration of shear stress over the section is called internal shear force. Okay, this is called internal shear force. in 우리말 내부 전단력. Okay, it's easy, right? And how about this? So certain distribution of normal stress. Actually, so if you integrate normal stress is equal to 0. For bending action, the internal axial force 내부 충격. Okay, so for the bending problem, the internal axial force is equal to 0. But look at this here. Actually, say this is very interesting problem, because we decompose the actual problem into two. So here, if you integrate the normal stress over the section, this is equal to 0. But here, see, if you integrate the normal stress over the section, it is not equal to 0. Then how much would it be? That should be equal to what? The force times sine theta, isn't it? Okay? Only for the beam problem, the integration of normal stress is equal to 0. Is it clear? And then also, so if you integrate the moment caused by small force, how do you define the small force? The stress, normal stress times the area. The small moment is defined as small force, normal stress acting on small area, times arm length, the y distance measured from the neutral axis. And then the total moment should be calculated by this way: stress dA y over the section, isn't it right? So now let's try to move y into here to make it fancy. Okay, is it clear? This is called internal bending moment. This is, we call it 내부 휨 moment, or simply we call just 휨 moment. Also same, even in English, sometimes we just simply we call it bending moment. So for beam problems, instead of talking about the detailed shear stress and the bending moment, so we use these internal forces, internal shear force and the bending moments. There is another reason, because the magnitude of normal stress is changing. That's why instead of handling with handling the normal actual distribution of normal stress, but instead of that we deal with the situation using the bending moment. Alright, so now let's talk about internal release in the beam problem. So for example, let's say I have a hinge, I have fixed support, and let's imagine that we have a hinge here. Then I want to connect another segment to the end of this cantilever. Then what's going to happen? So if you apply load, then because it's going to produce rigid body rotation, isn't it right? Then how do you prevent the rigid body rotation? To prevent the rigid body rotation, so we have to provide a roller support here, isn't it? Then it would deform in this way. It would deform, by the way, let's use different colors. It would deform like this. So if you apply load, then it would deform like this. Okay, isn't it right? So steel is stable, so we call it internal hinge. in 우리말 내부 힌지. Okay, so here typical example of internal hinge is given here. And then actually, the details of this structure part is complicated, isn't it right? So it is simplified like this. The beam is represented by a solid line. The internal hinge is represented by a circle, empty circle. This is simplification. Is it clear? And then here, because this hinge is support, at this point, because it's free rotation, the bending moment, internal bending moment is equal to 0 at this point, at hinge point. Okay, this is the characteristics of the internal hinge. How about another type? Let's consider this one. So if you consider this one, if you imagine a rotation from left hand side, then the rotation can be translated to the right hand side, isn't it right? Without any problem. But how about let's consider the shear deformation. If you consider shear deformation, maybe we have mismatch. We may have mismatch between the left hand side and right hand side, isn't it right? It is pretty obvious. So in this case, we call shear release. Okay, shear release. So we represent the shear release in this way. Okay, so at this point, the internal shear force is equal to 0. Okay, then how does it deform? It deforms like this, by the way. Actually, deformation of a beam with internal hinge, it would deform like this, and this guy will deform like this. This guy will deform okay. So we have jump jump in the displacement. So here we have jump in the rotation. Okay, this is jump operator, and then here we have jump in deflection. By the way, the displacement of beam is called deflection. Okay, the displacement, the lateral, the displacement of a beam in the lateral direction is called deflection. Okay, the deflection in 우리말 처짐. Alright, so this is a procedure for the statically determinate analysis. The first, we have to calculate the reaction for beam. So in the case of fixed support, we have reaction for the bending moment, and then we have reaction for the shear force. Okay, and how about the hinge? Where is it? Say for hinge. For hinge, we have reaction in the vertical direction and then the longitudinal direction. In the case of roller, we have reaction only in the normal direction to the plane of roller displacement. For the fixed support, we have 3 different reactions. Is it clear? And then first we calculate the reactions. Okay, reactions first, and then we consider a section in distance x, and then we calculate the required bending moment and shear force to satisfy. 원석이, the y indicate the distance measured from the neutral axis, but we haven't defined the concept of neutral axis. We'll discuss neutral axis later. Okay, 서원이, sorry. We calculate the magnitude of bending moment and shear force to satisfy the force equilibrium here, given here. We check the force equilibrium, the 3 conditions, to determine the internal forces. Okay, and then once we have internal forces, we can calculate. Once we have internal forces, then we can finish our analysis for this statically determinate analysis. Alright, so now let's talk about the sign convention. This is a sign convention for the normal stress, and when we discuss uniaxial loaded members, isn't it right? But in the case of beam problem, you know, the signs of normal stress is changing in the same cross section. That's the problem. The direction of normal stress is changing. That's why instead of using the sign convention for the normal stress, we define new sign convention using the bending moment. Okay, say let's imagine a beam structure. Let's imagine I have a beam. And then before we start any analysis, so we like to introduce a coordinate system, x and y direction here, isn't it right? So if you don't like this coordinate, maybe we can move the origin of our coordinate into here, x and y. Okay, and then let's imagine deformation, because this is beam problems, we must have in-plane deformation. So my beam will deform like this. I'm talking about very arbitrary deformation, isn't it? So now let's try to measure the curvature. If you measure the curvature, here we have positive curvature, isn't it right? The curvature is positive. And then also, at this part, we have the curvature is negative. So which one you want to choose the default positive deformation? A and B. What situation, which situation do you want to take as a default one? A or B? So anyway, we have to choose a state for the positive default situation. So which one you want to choose as the positive default one? A or B? Look at this, yeah. So here we want to talk about the general deformation, okay? And some part we have, convex deformation. Here we have convex, and then here we have concave deformation. Which one you want to choose as a default one? Convex or concave? Okay, Hyungmin이, why do you want to choose A as a default one? What's the reason that you want to choose A as the default one? Why do you have that preference? In any of variable, variable algebra or variable mechanics, we choose, positive one as a default. So once you have a coordinate system. So for example, so that's why by the same reason, so we want to choose the convex one, okay? We want to choose the convex one as a default one, okay? So then what produced this convex deformation? And then that convex deformation, this convex deformation would be produced by say bending moment A or bending moment B. What is correct? Does A produce this convex default curvature, or B bending moment produce default positive curvature? A or B? A or B? A, right? It is pretty obvious. That's why, okay? That's why we want to choose that bending moment as the default one. So I want to choose this is default positive. This is a sign convention. This is how we determine the sign convention for the bending moments. Okay, so now we determine, default positive bending moment. Default positive bending moment. This is default positive bending moment. Okay, so now let's consider general situation. So if you imagine the change of the distance dx, and then my bending moment also changes by dm, isn't it? So I must have little change in the bending moment. Okay, so let's say on this edge, okay, on this edge we do not have we do not have any traction here. Okay, say if you consider sum of bending moment is equal to 0 to satisfy the force equilibrium. Okay, force equilibrium, then we have this moment according to the sign conventions minus m and the plus m plus dm. It's cancelled, but it's not equal to 0. So which means we need additional component, isn't it right? So let's consider say initially it is equal to 0 here. But let's say if we have some distribution, okay, some distribution, we can consider two different kinds of distribution. Say dVA or dVB, and then these two would produce moment. So if you count this guy produce moment, you know, it's minus dx times dVA, and then this guy would produce the moment by dx dVB. Okay, if we want to choose dVA or dVB as default positive, under which one would cancel dm to satisfy the force equilibrium? 주승이. Yes, of course. Now I'm checking the bending moment with respect to this reference point. Thank you. So if you want to choose a positive value for dVA or dVB, then which one would cancel this dm to satisfy the moment equilibrium? A or B? Okay, 동현이, so you said A. How about other students? Do other students agree with 동현이? 형민이 agrees with 동현이. How about other students? 수민이 also. Yes, that's why. So if we want to use the VA as default positive, actually this guy cannot satisfy the moment equilibrium. That's why for the shear stress, okay, for the shear force, default direction of shear force is this. So we want to choose this is default positive for the shear force. Okay, so we want to choose this is default positive, and then this is for the sign convention for the bending moment. So in the textbook, the authors explain the sign convention for the shear force first. That's why it's confusing, but it is not. Okay, so first we determine the sign convention for the bending moment. The sign convention for the bending moment was, is followed by the positive curvature in the deflection of a beam in two-dimensional space. Okay, And to produce positive, to conform with the sign convention of the bending moment, so we need this sign convention for the shear force. Is it clear? You agree? Okay? It's really simple, right? Don't be confused with the sign convention for the material point. So for the material point, please compare with this. So for the material point, to define the default sign of shear stress, this is default positive, okay? This is material point, okay? This is for the material point, and this is for member, beam members. Okay, they are different, okay? So can I have the 5 minutes break?
예, 수업 중에 아직 안 와요. 예.
Is it clear? Alright, now let's talk about the relation between the distributed load and the bending moment and the shear force. So let's consider a small segment, a small beam segment. Say I have simply supported, and I want to consider a certain situation of the beam subject to uniformly distributed load. So we want to look at a small segment dx. Then in small distance, the change of distributed load is very small. That's why we want to approximate its magnitude by q. Okay, so according to the default definition of shear, the internal forces to distance of x, okay, at this point, so we have internal forces. Say we have one internal force called shear force, right? So Vx, shear force at position x, and then we must have bending moment at position x. And then if you change the distance by dx, then we must have another shear force Vx, but the Vx is changed by dV, isn't it? And then we must have another bending moment. This bending moment also changed by dm. Is it clear? Isn't it? Because we are looking at here. For example, here we want to look at shear force at position Vx dx, but this guy is approximated by Vx plus dV. By the not approximation, sorry, it's equal to this. And then the bending moment at position of x plus dx is given by mx plus dm. Okay, so now let's check the force equilibrium. So we want to check the force equilibrium for this. Okay, so first we want to check the force equilibrium in the vertical direction. So we have, I want to choose this is default positive direction, the upward direction, and then I have positive force V, and then I have negative force because this is distributed. So this is distributed, q times dx, but the sign is negative. And then this guy, is what? Now when we check the force equilibrium, although this is positive internal forces, but when we check the force equilibrium with respect to certain choice of coordinate system, it has minus sign, isn't it right? So it is cancels. That's why we obtain this. dv over dx is equal to minus q. What does it mean? The change of shear force between 2 points, point A and point B. Change of shear force between 2 points is integration of applied distributed load. This is nothing but just area of distributed load. For example, if you consider point A and point B, and then the change of the shear force between these 2 points A and B is equal to the area integration of applied load Q with the minus sign. Is it clear? Does it make sense? Now how about bending moment? So by the same logic, the bending moment should be equal to 0. Okay? So now let's try to calculate the bending moment. Say if we want to use this sign convention for the calculation of bending moment, this guy, what? This guy is equal to minus. And then how about this guy? So if we want to choose the left corner as a reference point for the calculation of bending moment, as using these questions. So this is the force Q times dx, and then the arm length is given by dx over 2. And then this is the moment development by v plus dv, and this is arm length, and then I have this bending moment. So it is cancels, and then this is what? dx is small quantity, but I have, square of dx. It's even smaller. That's why we can drop this because it's a second order small. And also the change of shear force should be small too. But small times small one, so we can drop this one too. So finally I have this equation. The rate of bending moment should be equal to the shear force. So again, integrating this equation, so I can obtain this equation. The change of bending moment between these 2 points then can be obtained by integrating the shear force between these 2 points. There's nothing but just the area of distribution of shear force. Is it clear? Okay. The change of shear force can be obtained by change of area of distributed load. And the change of bending moment between 2 points can be obtained by the area of shear force distribution. This is really important, okay? And how about the concentrated load? So concentrated load can be, represented by, this is very similar to this, okay? So this is a limiting case. So in the limiting case, dx is approaching to 0. This is nothing but just this. Okay, change of the shear force is given by just minus of applied force P in the vertical direction, downward direction, what I mean. And then if you look at this change of bending moment in this problem, because dx is very small, once dx is really small, there is no change of bending moment, okay, for the concentrated load. How about the concentrated moment? So if you apply the concentrated moment, so let's check this. If you apply the concentrated moment because of this couple, then there should be no change in the shear force. The V1 should be equal to 0, okay? And then because of this bending moment, to satisfy the moment equilibrium, the change of bending moment is the minus sign of applied moment. Alright, so let's do an example. It's very easy, okay? Okay. Now first, I have a beam. and then hinge support, and then I have a roller. Let's say I have a concentrated load, let's say 10, and then the distance to the load point from the left support is, for example, let's say 4, and then that distance is equal to 2. Okay, let's consider this situation. And first we have to identify the possible reaction. I told you that okay, I have to denote at this point. Let's say I want to denote this point A and point B. Alright, so let's identify the possible reactions. We must have FB here, FB, Y in the vertical direction, right? And then here hinge support. Also, I need to have FA, but in the vertical direction. And also, because this is hinge, it must provide resistance to the horizontal movement in the horizontal direction, FAX, isn't it? So now let's determine the reactions. Okay, so let's determine the reaction. So let's check the sum of force should be equal to 0. Then I have FAX plus nothing, right? So this should be equal to 0. This is equal to 0. And then how about force in the vertical direction? So FAY plus FBY minus 10 is equal to 0. Let's denote this is equation 1. And then now let's check the moment. So moment equilibrium with respect to point A is equal to 0. So arm length, from the reference point to this reaction is equal to 0. That's why this guy doesn't produce any moment to the choice of this reference point A. So we have to consider these two only, right? So this is equal to, that produce negative moment, 4 times 10. And then this produce positive moment, 6 times FBY should be equal to 0. That's why this equal to FBY is given by 40 divided by 6. Okay? And this is 20 over 3. Okay? So now let's determine the FAY. How do you determine FAY? FAY is equal to 10 minus FBY is equal to 10 minus 20 over 3. This is equal to 33 minus 23 is equal to 10 over 3. Okay? Yeah, we just determined the reaction here. Okay, let's mark reaction. This is equal to By is equal to 20 over 3, and this is equal to 10 over 3. We just determined the reaction. Now let's determine the shear force diagram. Okay, so let's determine the shear force diagram. Change of shear force. So we prepare a space for the discussion of shear force diagram. So if you look at the very left end of the beam, so if you look at the very left end of the beam, so we have force in the what? In the upward direction. So according to our sign convention, where's the sign convention? Here. According to sign convention, if you have upward force on the left side, then we want to call this is positive shear force, isn't it right? So in this problem, I have positive shear force. How much is it? The positive is 10 over 3. So I have positive shear force. At this point, its height is 10 over 3. And then is there any force? Yeah, there's no force, right? No force. No force means, according to this, look at this, according to this, the change of shear force is integration of applied distributed load, isn't it? So which means no change, okay? No change. No change. Constant line. Until what? Until we have any load in the vertical direction. So instead of distributed load, we have concentrated load. So if you have concentrated load, then we have change. We have change in the shear force, between the left hand side and right hand side of applied load by its negative magnitude. Then how much is it? It's 10. We must have total 10 change, okay? By the negative one, okay? The total change is by 10, okay? 10. And if you subtract, 10 from 10 over 3, the remaining is 20 over 3. And then finally we have force, upward force. So according to sign convention, the positive sign, according to sign convention, so we must have, if we want to have positive shear force, the force should be downward. Otherwise, if you have upward, it should be negative. So I have negative side. Okay? The sign is, the shear force sign is, this part I have shear force, this sign is positive, and then negative, minus sign. Positive and negative. Is it clear? And this is called shear force diagram. Okay, shear force diagram. Now let's try to calculate change of bending moment. Okay, it's also very easy. Okay, let's prepare a space to investigate the change of bending moment. Okay, and then we prepare a space. This is the two end points, and then I have one loading point. Okay, so at first we do not have any moment at the end, so which means my bending moment should be equal to 0 here. And then my shear force diagram is constant. My shear force diagram is constant here. Okay, then that means constant shear force diagram. The bending moment, change of bending moment is given by what? Given by, where is it? The integration of shear force diagram. Look at this. Integration of shear force diagram. The integration of constant one becomes what? Linear, isn't it, right? So I have positive, that's why I must have positive shear force. It should be linear. Is it clear? Then initially it was equal to 0. Now the change of bending moment can be calculated by the area. How do you calculate this area? This area is what? The length is given by 4. The area of rectangle is what? How do you calculate this? So 4 times 10 over 3, isn't it right? It's very easy. So 40 over 3. So the height should be the 40 over 3. Is it clear? And then let's look at this side. Then I also have non-zero shear force diagram, isn't it right? The change of bending moment between these 2 points should be calculated by the area integration of shear force diagram. In this time I have a minus sign. And then its length is given by what? 2. Okay, so let's calculate this area. 2 times 20 divided by 3 is equal to 40 over 3. But this sign is minus, isn't it right? The change should be calculated by this. Say we start with 40 over 3, but this change should be minus 40/3. That's why it becomes 0 here. Because shear force diagram is constant and the bending moment diagram should be linear. Okay? And the overall sign is positive. We call it bending moment diagram. Bending moment diagram. BMD. Bending moment diagram. Is it clear? It's easy, right? Do you have any questions regarding the calculation of shear force diagram and bending moment diagram? Okay, let's consider another example. So now consider this example. So I have simply supported beam, but it is subjected to uniformly distributed load. Say the very first step is, so we have to introduce a coordinate system. So I want to choose this as x coordinate, right? And then I have uniformly distributed load Q. Okay, say I want to denote this point A and point B, and then its length is equal to L. And it is trivial to discuss how to calculate the reaction here. The reaction is equal to what? How much is it? A half of QL. So a half of QL. Okay. So now let's discuss shear distribution of shear force diagram. Shear force diagram. Okay, so let's start from the left hand. I have upward a half of QL. According to sign convention, this is positive, isn't it, right? The height is a half of QL. Okay, my shear force diagram is constant. So the change of shear force between 2 points is in area integration of distributed load. Okay, so let's try to calculate the change of shear force. The change of shear force between point A and point B, this is equal to del V is equal to what? Del V is equal to minus Q times L, isn't it? So my shear force V at point B is equal to shear force at point A plus the change of shear force. The V shear force at point A is equal to a half of QL. And then the change of shear force is given by minus QL. This is equal to minus a half of QL. Is it clear? Okay. So my shear force should be on this side, is on minus side. Here. And then because the load is uniformly distributed, my shear force diagram should be linear. Just draw a straight line. And then, you know, here we have positive shear force and I have negative shear force. Negative internal shear force. Is it clear, right? The next step is, let's try to construct the bending moment diagram. Bending moment diagram. So this, in many cases, we say that we construct the shear force diagram or we construct bending moment diagram. In 우리말, the construct can be translated to the 작도하다, okay? 작도하다. Okay, now we prepare the space for the bending moment diagram here, okay? We have this. And then if you look at the left corner, let's start with left corner, there's no concentrated moment. That's why the bending moment should be equal to 0 here. here, isn't it? Also, if you look at the right corner, the bending moment should be equal to 0. Alright, so now let's look at the shear force diagram. And then if you look at the shear force diagram, my shear force diagram is linear, isn't it? But its shape is what? Triangular. So can you calculate the area of triangle? Yes, it is very easy to calculate. So if you consider only this part, okay, only consider the upper triangle, then up to here, right? Probably up to here. The change of bending moment up to the center is what? How do you calculate this? The change of bending moment up to the center is, sorry, the m is what? The integration of this triangle, the area of triangle. So a half of the width is equal to a half of length L, and it's the height of the shear force, or half of QL. So many people are looking for me. This is equal to or eighth Q times L square. Okay, so initially my bending moment it was equal to 0. By the way, its sign is positive, right? Look at this. So the height should be equal to 1/8 Q times L square. Now let's talk about the shape of the bending moment diagram. Look at this. Shear force diagram is the derivative of the bending moment. Look at this. My shear force value, shear force diagram is the derivative of the bending moment. Okay, look at this. My shear force diagram is linear. The integration of linear becomes what? Quadratic. It's in second order. But if you look at the rate, initially we start with a bigger rate, and then finally the rate becomes 0, because the shear force value is the rate of bending moment. Okay, dm over dx, this is the rate of the bending moment. If the shear force is equal to 0, my rate of bending moment is equal to 0, which means it reaches to the maxima. Initially it starts with larger slope. This slope is V, and then we have larger slope. We start with larger slope, and finally the slope becomes 0. Okay, and then we have same area. Okay, same area but different sign. That's why for this part we have this another second order curve. Is it clear? And the sign is positive. You understand? Okay, that's why we have this equation. And next Monday, my TA would discuss some more examples, problems with you guys to help you guys to understand the nature of the shear force diagram and the bending moment diagram. And then we'll take our midterm examinations up to this part. We should be able to construct the shear force diagram and the bending moment diagram. So let me start my lecture in this week. So we'll cover up to here in the midterm examinations. Do you have any questions? Any questions? Any questions? So let me start my lecture if you don't have further questions. 혹시 n is equal to 0? 수민이, it is obvious. For example, let's look at here. So we want to consider in beam regarding the discussion of beam. So we want to consider a situation that, so we want to say even in this arbitrary condition of loading. So we want to decompose this problem into these two, one for bars and the one for beams, because there is no external loads correspond to the longitudinal direction for beam mechanisms. That's why the integration of internal force should be equal to 0. Any other questions? Okay, then I'd like to stop my lecture here, and then everybody's good luck in your midterm examinations.